We have our third problem here, and we're told to find dy dx as a function of x using logarithmic differentiation, and as with the first problem, we are asked not to simplify. Part A is a quotient. We have y equals a ratio, basically, of these two terms. So how do we go about solving this? I have written here in this corner a version of this. Notice, in place of my 3x to the fourth plus 2, I simply have an a. Instead of 2x minus 1, I have a b, and I have a c instead of this. And the reason for that is to basically have a shortcut to help us solve this problem. Now, what is logarithmic differentiation about? That basically is a way for us to take derivatives by simply taking logs of both sides and then using the properties of logs to make the problem easier. If we were to find a derivative of this problem without logarithmic differentiation, it's going to be a lot tougher because we have so many powers here. But remember, a logarithm is itself a power. So that's going to help us with this problem, with simplifying the arithmetic and the whole math behind it. Let's go ahead and expand what I've written on this side here. If I have the natural log of a to the fifth and b cubed over c to the 1/2. Based on the properties of logs, we know that what we actually have is those two can be added of a to the fifth plus the natural log of b cubed minus the natural log of c to the 1/2. We may or may not have parentheses around here. It doesn't make a difference. Now, using this formula, let's go ahead and substitute our a, b, and c where they simply mean these terms here. Let's do that. I'm also going to skip a step. I will use the property of logs we just talked about, and I'm also going to take the logs of both sides because that's the whole point of logarithmic differentiation. And recall, I did say I was going to skip a step. So what I did to get from here to here was I took the natural log of both sides, and I applied the formula which I just erased. I basically have the same thing, but all that changed is the powers simply became coefficients of the natural logs. They simply are being multiplied by it because that is our exponent property of logs. A natural log is a power. All right, so now when we have this step, we essentially can no longer use any properties of logs. So the next step is to take derivatives. All right, so now we're going to take the derivatives as mentioned. So another way to write this is simply dy dx over y. 1 over y times the derivative of y with respect to x. Now that equals the derivative of the right-hand side with respect to x. What is that? That's going to be, now 5 is a constant, and remember our formula for taking derivatives of natural logs, it just becomes 1 over the whole quantity in here times the derivative of what's inside. So 1 over 3x to the fourth plus 2 times the derivative of this. What's that? 4 times 3, 12. That becomes a 3, so 12x cubed. Don't forget we had 5 here, so it's going to be 5 times 12x cubed. Plus So we have a coefficient of 3. I know I'm going to have a 3 times 2x squared minus 1. And then derivative of this would be 4x minus, that goes in the denominator, 3x plus 1. I have a half here. Derivative of that is 3. And we're almost done. We're asked to find dy dx as a function of x, so it has to be solved explicitly in terms of x. There can't be any y's on the same side. The last step is to simply multiply this y by both sides, and that'll be the final answer. Now, when I multiply y by the right-hand side, I can't simply write a y, because as mentioned, we must have it as a function of x. There can't be any y's in the equation on the right-hand side. So, what is y? Well, this is y in terms of x. We need to take all this and write it in. So it's going to have to be 3x to the 4th. It's a lot to write, but we're going to have to make it work. Times 2x squared minus 1 all cubed over the denominator, 3x plus 1 to the 1/2, that's y, times what we had earlier, which is 5 times 12x cubed, that's 60x cubed, over 3x to the 4th plus 2 is 12x over 2x squared minus 1 minus 3/2 over 3x plus 1. And that's our final answer. We're asked not to simplify, thankfully, or else this problem would be a nightmare. It would be pretty hard to simplify, but we don't have to. We're just being tested on our knowledge of derivatives, especially logarithmic differentiation. Thank you, that's part A. For part B, we have y equals the natural log of x raised to the x power. So it's basically going to be the same concept. We go about solving this the same way. We take the log of both sides, take the derivatives, and then figure out what dy dx is. So we have natural log of y equals the natural log of the natural log of x raised to the x. So we have the natural log of a natural log. Using the power property of logs, I can make this x times the natural log of the natural log of x. Now I take the derivative of both sides. When we're done, when we've exhausted the properties of logs, so there's no other properties I can use here. So now I'm ready to take the derivative of both sides, and that gives me dy over dx times 1 over y, but I'm just going to skip the 1 over y because I know I'm always going to have that. So I might as well just multiply the y by the right-hand side. That equals y times the derivative of this. What's the derivative of x times the natural log? Well, first, remember I always say, in math, try to look at the big picture. That's key. It's really huge. And then we try to work our way in. We have a product here, x times something else. We don't worry about the fact that we have a natural log within a natural log. That comes later. Now, what's key is it's x times. So we know we're going to have to use the product rule because we have two factors being multiplied, and the product rule tells us that the quantity uv prime equals u times v prime individually plus u prime times v. So u is x here, our first term. So let's be able to identify them. Our u will be x, and then our v is obviously the natural log of the natural log of x. So u, so what's the derivative of this? Well, our formula tells us derivative of any natural log is just 1 over what comes after the natural log times the derivative of what's after. So that's going to be 1 over the natural log of x times the derivative of the natural log of x, which is also just 1 over x. So I'm just going to put the x over here. So we're done with that. Now let's figure out the derivative of u. Derivative of x is 1 times v, so the whole quantity, natural log of the natural log of x. Okay, are we done? No, we're not. The only reason we're not done yet is because we have a y here, and we don't want that. We must have dy dx as a function of x, not y. So all we have to do is simply substitute dy dx equals natural log of x to the x power times 1 over, keep in mind this x and this x will cancel, whereas not to simplify, but it just makes the problem easier to write. There are just fewer x's to bother about. Plus natural log of the natural log of x. And that would be our final answer. For number 4, part A, we have to find the integral of x squared over x cubed plus 1 dx. The best way to solve this problem is by u-substitution. And why is that? Because we have x cubed plus 1 in our denominator. And if I make that u, I know if I take the derivative of u, I'm going to have its derivative is contained in the problem. So in other words, the derivative of x cubed plus 1 is 3x squared, which is contained. There's a form of it that's contained in the integrand. So let's go ahead and write that. Let u equal x cubed plus 1. Du is going to be 3x squared dx. You see we have our x squared dx, so it looks like du. Always pick your u in such a way that when you take the derivative of it, you have a form of du contained in your integral. So, what do I have to do to du to get x squared? Well, I simply divide by 3 because a third of it is there. So 1/3 du equals x squared dx, and that's perfect. That's exactly what you want. A lot of math is about manipulating the problem to fit exactly what you're looking for. You want to make the problem easier for yourself. So based on that, what we have here is the integral of 1/3 du over u. That's our u, and that's our 1/3 du in the numerator. It becomes 1/3 the integral of du over u, and we know the integral of du over u is simply the natural log of u, so that becomes 1/3 the natural log of u plus c. Now, u would define to be x cubed plus 1, so let's go ahead and substitute that. That gives us 1/3 the natural log of x cubed plus 1 plus c. For part B, we're asked to find the integral from 0 to pi over 8 of 2 to the tangent of 2x times secant squared 2x dx. Again, we want to pick our u such that when we differentiate, our answer, our derivative, is contained within the integrand. Let's see what I mean here. Let's make u equal to the tangent of 2x. So du is going to be 2 secant squared 2x dx. So we almost have that. We just don't want 2. We want 1 secant squared dx. Just divide by 2. So half du equals secant squared 2x dx. That's what we have here. That's our half du, and this is 2 to the u. So what we have here then is the integral. Now we have to be careful. Our limits of integration are going to be different based on u. We're going to find out those in a second. Now, 2 to the u times 1/2 du. What's u of 0 going to be? Let's figure that out. If u is tangent of 2x, u of 0 then is going to be 0, because tangent of 0 is 0. What about u of pi 8? Pi over 8. Well, pi over 8, double it, pi over 4, tangent is 1. So, Those are our new limits. 0 in place of 0, I still have my 0. In place of 0, I still have 0. In place of pi over 8, I have 1. So that's what we need to integrate now. These are our limits. Let's figure what this is. This is a constant. Let's bring that out. We have 1/2 times the integral from 0 to 1 of 2 to the u du equals, according to our formula, whenever we take integrals with a constant base and an exponent, our formula tells us that we're going to have, should give us 2 to the u over natural log of 2. Now this half still applies, so let's bring that here, and we're evaluating this from 0 to 1. Let's move over here. So 2 to the u over 2 natural log of 2 from 0 to 1. What does that give us? When I substitute a 1 here, I have 2 over 2 times the natural log of 2. So 2 over 2 times natural log of 2. The two 2's are going to cancel themselves. That just leaves 1 over natural log of 2. When I substitute a 0, I get 2 to the 0. That's a 1 times 2 natural log of 2. So 1 over 2 natural log of 2. Notice I have a natural log of 2 in both cases. So those can be factored out, leaving 1 over natural log of 2 times the quantity 1 minus a half. And what's 1 minus a half? 1/2. What I have is simply 1/2 times 1 over natural log of 2. And then using our property of logs, where we can just combine powers, so this 2 can just become a 2 squared here using the power property. So our final answer then is going to be, we have 1 over natural log of 4. 1 over the natural log of 2 squared, which is 4. Part C, the integral from 0 to square root of pi of x times the tangent of x squared over 4 dx. This is also going to be a u-substitution problem. And why is that? Again, it's because whenever we differentiate one of the terms, our derivative is contained in the integrand. Let's see what we mean. Let's let our u be 1/4 x squared. Du then is going to be 1/2 x dx. I have a half x dx here. Here I have an x dx. So all I have to do is simply double du. So 2 du equals x dx. Now, for our limits, let's figure those out. U of 0, so 1/2 of 1/4 of 0 squared is simply 0. What about u of radical pi? If I were to square the square root of pi, I get pi, then take 1/4 of that, that's just pi over 4. So what we have is the integral from 0 to pi over 4 of 2 du times the tangent of u. Here's our u, and x dx is 2 du. When we integrate that, so r2 is a constant, let's bring that out, leaving 2 here, times the integral from 0 to pi 4ths of tangent u du. The integral of tangent is the natural log of the absolute value of secant. So let's go ahead and substitute. This equals 2 times the natural log of the absolute value of secant u, evaluated from 0 to pi over 4. The secant of 0 is 1. So whenever I plug this in for 0, I get secant of 0. Natural log of 1 is 0. So we know we're going to be subtracting 0 for the lower limit. For the upper limit, I have secant of pi over 4. Remember, pi over 4 is 45 degrees. Being able to interchange between radians and degrees is helpful. So the secant is going to be the reciprocal of cosine of pi over 4, which is going to be 2 over radical 2. So this should give us 2 times the natural log of 2 over the square root of 2. Now remember our property of logs. This 2 here can become a power. So that simply becomes the natural log of 2 over radical 2 quantity squared. When we simplify, we have the natural log of 4 over 2, which is 2. That's it. Natural log of 2 is our final answer. For part D, we have 1 over x times a log raised to a fractional power, 1/3 power. So let's figure out how we're going to do u sub here. Again, I'm going to do u substitution because I know if I take the derivative of a log, I get a fraction. A fraction is going to be involved. So I'm going to pick my u to be log base 10 of x. That gives du is going to be 1 over x times 1 over the natural log of 10 dx. And if I were to multiply both sides by the natural log of 10, because it's a constant, I get natural log of 10 du equals 1 over x dx. That's exactly what we have. So this problem then becomes natural log of 10 times u to the 1/3 du. Remember, natural log of 10 is constant. We take that out. And to solve this, we know we are going to simply add a 1 to the current exponent, becomes 4/3, and then the reciprocal divides by that, multiplied by natural log of 10, so that gives us the natural log of 10 times 3 over 4, u to the 4/3 plus c. That equals the natural log of 10 times 3/4. Now let's back substitute for u. Log base 10 of x to the 4/3 plus c. And if we went ahead and differentiated this solution, we will see it gives us our original problem back, our original integrand back.